All right, let's dive into one of the biggest detective stories in all of science. It's a story that completely upended how we think about reality itself. We're talking about the true nature of light, and it all kicks off with one very simple question.
So picture this. You've got a barrier, and in it are two incredibly narrow slits, right next to each other. Now, you shine a light through them onto a screen on the other side. Common sense tells you what you should see, right? You should get two bright lines of light on the screen, basically shadows of the slits. But that's not what happens, not even close.
You get this, a whole series of bright and dark stripes. Somehow, two slits create many lines. And that right there, that's the mystery we're here to solve. Why on earth does light behave in this completely bizarre and unexpected way? So our investigation really begins with this pattern. It's our number one clue, and it's telling us something incredibly profound about what light actually is. You know, scientists have a name for this pattern. It's called an interference pattern. And that name, interference, is a massive hint. It suggests that whatever is passing through those slits is somehow interfering with itself. So to crack this case, we need to take a quick detour and talk about the secret lives of waves. So let's just forget about light for a second. Let's talk about waves in general, like ripples on a pond, because the way they behave when they meet is the absolute key to this whole mystery. There's this one fundamental rule that all waves follow. It's called the superposition principle, which sounds super complicated, but it's not. It just means that when two waves cross paths, you literally just add them together to figure out what the new combined wave looks like. And this simple addition can lead to two totally different results. First, you can get what's called constructive interference. This is the intuitive one. It's when the peak of one wave meets the peak of another. They join forces, they reinforce each other, and you get a brand new, bigger, more powerful wave. Just think of two boat wakes hitting each other and making one giant wave. But then, there's this. This is where it gets really wild. You can also have destructive interference. This happens when the peak, the high point of one wave meets the trough, the low point of another. And when they meet, they can completely cancel each other out. You get nothing, just flat water. It is literally possible for two waves to combine and create absolute stillness. Okay. So if light is a wave, and waves can do this canceling out thing, why isn't my room a crazy zebra pattern of light and dark? Why don't the two lamps on my desk create this pattern on the wall? Well, it turns out light is a bit picky. It has to follow some very specific rules for this to happen. For you to see a stable, visible interference pattern from light, two conditions have to be met. First, the light has to be coherent. Think of this like all the light waves marching perfectly in lockstep. Their peaks and troughs are all aligned and they stay aligned. Second, the light has to be monochromatic. That's just a fancy way of saying it has to be one single, pure color, which means it has one single wavelength. And that right there is why we don't see this in everyday life. A regular light bulb is an incoherent source. It's just spewing out a chaotic jumble of different wavelengths, all out of step with each other. Now, they are still interfering, but the patterns are changing so incredibly fast, we're talking less than a billionth of a second, that our eyes can't keep up. We just see it all averaged out as a nice, smooth glow. And this brings us to the big breakthrough. Back in 1801, a scientist named Thomas Young came up with this absolutely brilliant experiment. At the time, everyone, including Isaac Newton, thought light was a particle, but Young's experiment was about to prove that wasn't the whole story. Young's setup was just genius in its simplicity. He started with a single source of pure colored light. He passed it through one slit first, just to get a nice, clean, orderly wave. And then that single wave hits the two slits. This is the crucial move. Because both slits are being hit by the exact same wave at the exact same time, the two new little waves that emerge are perfect, synchronized copies of each other. They're coherent. And when those two coherent waves spread out and overlap, you get the pattern. So now we have all the clues. We know light can act like a wave, and we have an experiment that produces that classic wave interference pattern. So let's decode exactly why those bright and dark stripes appear right where they do. The entire pattern comes down to one simple concept: path difference. For any spot on that screen, the wave from one slit has to travel a slightly different distance to get there compared to the wave from the other slit. And that little bit of extra distance it has to travel, that's what we call the path difference. And everything depends on that path difference. If the extra distance is exactly one full wavelength,
or 2 full wavelengths, or 3, and so on, the waves arrive at the screen perfectly in sync, peak to peak. They interfere constructively, build each other up, and create a bright spot. But if that path difference is a half a wavelength, or 1.5 or 2.5, the waves arrive perfectly out of sync, peak to trough. They interfere destructively, cancel out, and you get a dark spot.
So here's the bottom line. The fate of the light at any point on that screen, whether it ends up bright or dark, is determined entirely by the path difference. It's just simple geometry controlling this incredible, complex pattern.
Let's just make this super concrete. Let's pick one of those bright spots on the screen and see what the math actually tells us is happening there.
Well, when you run the numbers for one of these bright spots, you find that the path difference divided by the wavelength of the light equals 3. Exactly 3.
So what does that mean? It means the extra distance one wave had to travel to get to that spot was precisely 3 full wavelengths. So the waves arrive perfectly in sync, peak to peak. They reinforce each other, and the result is a bright fringe. It works.
And there you have it. The only way to explain that strange pattern of light and dark is if light is a wave. Young's experiment was this landmark moment, this beautiful proof that settled the debate for a long, long time. Light is a wave, not a particle. Case closed. Or was it?
For decades, everyone thought the case was closed. But science always keeps asking what if. And someone asked a great one. What if you turn the light source down, way, way down, so that only one single particle of light, one photon, goes through the experiment at a time? I mean, there's nothing for it to interfere with, right? It's all by itself. So the pattern should disappear. Shouldn't it? Well, that opens up a whole new mystery. One that takes us right to the bizarre, mind-bending heart of quantum mechanics. But that is a story for another explainer.